On January 30th, 2026, a patch of the sun's surface began to twist. It wasn't much to look at first. A dark freckle on a bright disk, 93 million miles away. The kind of thing that shows up and fades out without anyone outside a handful of solar physicists ever noticing. NOAA gave it a number. Region 4366. Nobody watching it that first day had any reason to think it would become the most talked about patch of the sun all year. Then it started to grow. Within days, Region 4366 had swollen to 9 times the surface area of Earth. Stretched end to end, it measured roughly 10 Earth diameters across. It got big enough that people watching a solar eclipse with the right protective glasses could see it with their own eyes. A dark blemish on the face of our star, visible without a telescope. Spaceweather.com had a blunt name for what it had become. A solar flare factory. Factories produce things. This one produced X-rays, ultraviolet radiation, and a level of magnetic tension that had been building since the region first tore itself out of the sun's interior. Sunspots are magnetic knots, places where the sun's internal magnetic field pokes up through the surface and tangles itself into loops and arcs. The bigger and more twisted the knot, the more energy it can store, and the more violently it releases that energy when the knot finally gives way. Region 4366 wasn't just big, it was complicated in exactly the way that makes physicists nervous. And on the night of February 1st, it let go. What happened next was the biggest solar event of 2026. But the more interesting question isn't what Region 4366 did. It's what almost happened and what scientists now say might still be coming. So let's start at the beginning. What actually happens when a small, unremarkable sunspot turns into a factory for the most violent explosions in the solar system? By January 31st, Region 4366 was already restless. A string of C-class flares rippled out of it that evening. Nothing dramatic, the kind of background noise the sun produces constantly. But by early February 1st, the noise sharpened into something else. M1.7, M1.0, M1.9. 3 flares in quick succession, each one a notch stronger than ordinary solar weather. Then within 2 hours of each other, M6.6 and M6.7. The region was climbing, and it wasn't slowing down. At 12:33 UTC on February 1st, it crossed a threshold. An X1.0 flare tore out of Region 4366, the first X-class event of the day. X-class is the top rung of the scale scientists use to measure flares, and crossing into it means something has gone seriously wrong with the magnetic field holding the region together. But X1.0 was only the opening act. The region kept building through the day. More M-class flares. More warning signs. Solar physicists watching the region's magnetogram data could see the tension accumulating in real time, the way you can watch a storm cell darken on radar before the first thunderclap. And then, at 6:57 p.m. Eastern Time, 23:57 UTC, it happened. An X8.3 class flare erupted from Region 4366. It was instantly the strongest flare of 2026. According to data compiled by Space Weather Live and reported by Scientific American, it was the brightest flare the sun had produced since October 2024, and it ranked among the 20 most powerful flares recorded since 1996. 3 decades of data, and this event landed in the top 20. The effects reached Earth almost immediately. Light doesn't wait. X-rays and extreme ultraviolet radiation from the flare travel at the speed of light, and within minutes of the eruption they were slamming into the upper layers of Earth's atmosphere. Radio operators over the South Atlantic and parts of South America and Africa watched their signals degrade as the flare's radiation washed over the daylight side of the planet. It wasn't catastrophic. But it was immediate, and it was real, and it happened faster than most people can react to anything. For a moment, Region 4366 had the world's solar physicists' full attention. The question on everyone's mind was simple. What happens next? To understand what came next, you have to understand what a solar flare actually is, and more importantly, what it isn't. A flare is not a solid object hurled into space. It's a release. Deep in the sun's atmosphere, magnetic field lines get twisted and stressed, the same way a rubber band gets stressed the more you wind it. Eventually, the tension becomes too much. The field lines snap and reconnect in a new, lower energy configuration, and the difference between the old energy and the new energy has to go somewhere. It goes out as light, X-rays, ultraviolet radiation, a burst of pure electromagnetic energy unleashed in minutes. Think of it less like an explosion and more like a whip cracking. The whip doesn't launch a chunk of itself at you. It releases the tension stored in its length all at once, as a wave that travels down its body and snaps at the tip. A solar flare works the same way, except the whip is made of magnetic field lines the size of planets, and the crack of the tip is a burst of radiation that crosses 93 million miles in 8 minutes flat. That radiation is what caused the radio blackouts. It slams into Earth's ionosphere, the electrically charged layer of our upper atmosphere, and increases its ionization, particularly in a lower band called the D layer. That extra ionization absorbs high-frequency radio signals before they can bounce properly, which is why pilots, ham radio operators, and maritime communications systems felt the X8.3 flare within minutes of it happening, even though nothing physical had crossed the gap between the Sun and Earth yet. None of this touches human bodies directly. Earth's atmosphere absorbs the X-rays entirely before they reach the ground, which is why the flare itself poses no danger to anyone standing outside, looking up. The danger, if there is one, lives entirely in the systems we've built that depend on clean radio signals and stable electrical currents. A flare doesn't hurt people, it hurts infrastructure. And infrastructure, unlike people, can't duck. Because here's the distinction that matters: a flare is light. A coronal mass ejection, a CME, is matter. It's an actual cloud of solar plasma, billions of tons of charged particles physically flung outward from the Sun. CMEs move far slower than light, typically somewhere in the range of hundreds to a couple thousand kilometers per second, which means they take anywhere from a day to several days to cross the distance to Earth, if they're heading our way at all. A flare tells you the Sun just did something violent. A CME tells you whether that violence is coming for you. So the question after region 43666's X8.3 was whether a CME had come with it, and whether it was actually aimed at us. This is where the story gets more interesting than a simple biggest flare of the year headline suggests. Because for a while it looked like the answer was going to be no. Early analysis suggested the X8.3 flare hadn't produced a particularly dense coronal mass ejection. Without a big cloud of plasma riding behind the light, there was no reason to expect a major geomagnetic storm. Scientists studying the imagery from spacecraft like SOHO watched closely, but the initial read was almost anticlimactic. The Sun had thrown its punch and Earth might just watch it sail past. But region 4366 wasn't finished. Its magnetic structure had become what solar physicists call beta-gamma delta, a technical way of saying the region's magnetic polarities were mixed together in the most complex, stressed configuration possible. That kind of structure doesn't calm down quickly. As the region kept rotating toward the center of the Sun's visible disk, directly toward Earth, conditions stayed primed for more eruptions, and for CMEs that might actually be pointed our way. 4 days after the X8.3 on February 4th, the magnetic cloud from that flare arrived at Earth. NOAA's modelling had predicted it would pass mostly to the north and east of our planet, a glancing blow rather than a direct hit, and that's largely what happened. The cloud brushed against Earth's magnetosphere, and the result was a minor geomagnetic storm, a KP index of 5. In Belgium, ground stations recorded a brief matching spike in the local magnetic index. It was enough to register. It wasn't enough to produce aurora visible from most of Europe. Meanwhile, region 4366 kept firing. Another strong flare on February 4th, an X1.5 on February 5th. By the time NOAA tallied it up, the region had produced 21 C-class flares, 38 M-class flares, and 5 X-class flares since it first emerged on January 30th. A little over a week of activity, 5 separate X-class eruptions. And in the end, the strongest of them delivered little more than a shrug from Earth's magnetic field. So was that it? Was the biggest solar event of 2026 really just a near miss that fizzled into a KP5 storm and a few disrupted radio signals? To understand how close that actually was and how differently it could have gone, it helps to look at what happens when a flare of similar strength doesn't miss. In May 2024, a different active region numbered 3664 produced a string of flares up to X8.7, almost identical in strength to region 4366's headline event. But 3664's coronal mass ejections were aimed almost squarely at Earth. Several of them arrived in close succession over just a few days. The result wasn't a KP5 brush. It was a full G5 extreme geomagnetic storm, the highest rating on NOAA's scale, with a KP index that hit 9, essentially maxed out. Aurora were reported as far south as Mexico and Florida, hundreds of miles outside their normal range. People who had never seen the northern lights in their life stepped outside and watched the sky turn green and red. Go back further, to March 1989, and the picture gets even starker. An X15 flare, nearly double the strength of region 4366's biggest eruption, triggered a geomagnetic storm so severe it took down Hydro-Quebec's entire power grid. 6 million people lost electricity within seconds in the middle of a Canadian winter, because the induced currents from the storm overwhelmed transformers hundreds of miles from where the flare actually happened. Communication systems degraded globally. The onset was almost instantaneous, faster than the grid's operators could react. Same basic physics, same category of flare, give or take, wildly different outcomes. The difference wasn't really about how powerful the flare was. It was about where the resulting cloud of plasma happened to be aimed and how directly it lined up with Earth's own magnetic field when it arrived. Think of it like throwing a stone into a pond from the same height, the same arm, the same force, every time. Most of the ripples spread out and die off somewhere in open water. But every so often, the stone lands close enough to shore that the ripple reaches the bank with enough energy left to actually move something. The stone doesn't change, the distance to shore does. Region 4366 produced flares in that same X8 class range as both of those historical events. It just happened to send most of its material past us instead of into us. That's not a law of physics, that's a coin flip that landed the right way. Which raises an uncomfortable question. If the coin can land the wrong way, how often does it? And is there any way to know when the odds are stacked against us? That question sat mostly unanswered for decades because major flares are notoriously hard to predict. They erupt fast, they erupt with little warning, and the exact moment a magnetically stressed region will finally snap has always been close, too impossible to forecast, with precision. But in 2026, a team of researchers published something that reframes the entire problem. Not by trying to predict the moment, but by predicting the odds. The study comes from Dr. Victor M. Velasco Herrera at the National Autonomous University of Mexico, working with an international team of scientists from the United States, Hungary, Turkey, Russia, the Czech Republic, and China. It's titled A New Method for Probabilistic Spatio-Temporal Forecasts of Solar Soft X-ray S-Class Superflares, and it was published in the Journal of Geophysical Research, Space Physics. An S-Class superflare isn't the kind of thing region 4366 produced. It's an order of magnitude bigger. The classification kicks in above X10 more than the strength of the 1989 Quebec event and roughly the strength you'd need to genuinely threaten modern infrastructure on a continental scale. If region 4366's X8.3 was a factory running at full capacity, an S-Class event is the factory's foundation giving way. These events aren't measured with the same instruments amateur skywatchers use. Because Earth's atmosphere absorbs solar X-rays completely before they reach the ground, scientists rely entirely on satellites parked in geostationary orbit to catch them. Watching the sun continuously, in wavelengths our eyes were never built to see. The researchers went back through nearly 50 years of satellite data, from 1975 to 2025, collected by the GOES fleet of geostationary weather satellites. Combing through it, they identified 37 S-Class superflares across that span, scattered through every completed solar cycle since the late 1970s. And that's where the study's most striking finding shows up. Every solar cycle since the late 1970s produced at least one Earth-directed S-Class superflare. Every single one. Except this one. Solar cycle 25, the cycle we're currently living through, hasn't produced one yet. At least not one aimed at us. Is that reassuring? On the surface, maybe. But the researchers don't read it that way. They read it as a gap, a cycle that statistically is overdue. So how do you forecast something that's inherently unpredictable moment to moment? The team's answer was to stop trying to predict the moment at all. Instead of asking, when exactly will the next superflare happen, their model asks a different question. When is the sun statistically more likely to produce one, and where on its surface is that most likely to happen? It's less like predicting the exact second lightning will strike and more like knowing which afternoons a thunderstorm is likely to roll through, and which side of the valley it'll probably hit. Digging into decades of flare and sunspot data, the team found two overlapping rhythms hiding in the noise. A shorter cycle of roughly 1.7 years and a longer one of about 7 years. On their own, neither cycle tells you much. But when the peaks of both rhythms line up, like two waves crossing and briefly reinforcing each other, the researchers found the odds of a superflare spike sharply. Picture two metronomes ticking at slightly different speeds. Most of the time their beats fall out of sync, scattered, unremarkable. But every so often, the beats land together, and for a brief window, the combined tick is loud enough to notice. That's the pattern the team found buried in the sun's activity. Using that pattern, the model produces two flagged danger windows for solar cycle 25. The first runs from mid-2025 through mid-2026, centered on the sun's southern hemisphere, specifically between 5 and 25 degrees south latitude. The second runs from early to mid-2027 and shifts north, focused between 10 and 30 degrees north latitude. That first window is the one we're standing inside right now. It's worth being precise about what these windows are and what they aren't. They aren't a countdown, and they aren't a guarantee. A high probability window can pass quietly, the way a hurricane season can end without a single major storm making landfall. What the model gives forecasters isn't certainty, it's something closer to a heightened state of alert. A reason to watch specific stretches of the sun's surface more carefully than they otherwise would, during specific stretches of time. For satellite operators, grid managers, and space agencies planning astronaut activity, that kind of advance notice, even measured in months rather than minutes, is worth a great deal. The model isn't just a theoretical exercise either. While the researchers were building it, they found supporting evidence sitting in data most people never see. Back in May 2024, several enormous flares erupted on the far side of the sun, the hemisphere permanently hidden from Earth's direct view. Estimated at X11.1 and X16.5 class, based on the data available, these were true S-class events, superflares by any definition. They simply happened to occur on the side of the sun facing away from us. No one on Earth felt them. But they happened, at exactly the kind of magnitude the model is built to flag, and close to the same period the researchers were studying. It's a reminder that superflares aren't hypothetical. The sun produces them. The only open question is whether Earth happens to be facing the right way when it does. There's one more piece of context worth sitting with. NASA and NOAA estimate that solar cycle 25 reached its solar maximum, the peak of the sun's roughly 11-year activity cycle, back in October 2024. And historically, the 2 years following a solar maximum are exactly when this kind of sporadic, intense magnetic activity tends to show up. Not necessarily the peak of overall sunspot numbers, but the peak of unpredictable violence from individual regions. Region 4366, in that sense, wasn't an anomaly. It was almost on schedule. So where does that leave us? Standing here in 2026 with Region 4366's flares already fading into the background, and a new forecasting model quietly running in the background of solar physics labs around the world. Region 4366 gave us a preview. 5 X-class flares in about a week, one of them among the 20 strongest in 30 years, and in the end, a KP5 storm that most people never even noticed. It's tempting to read that as proof the danger is overstated. But the same physics that produced a glancing KP5 storm in February also produced a G5 extreme storm in May 2024 and a continent-wide blackout in March 1989. The flare strength wasn't wildly different in any of those cases. The outcome depended on geometry, on timing, on a CME's trajectory lining up or not with Earth's magnetic field. Region 4366's material missed. It didn't have to. And according to the Velasco-Herrera team's model, we're currently inside one of only 2 windows this entire solar cycle where the odds of something much bigger, an S-class superflare, are meaningfully elevated. That window runs through the middle of 2026. After that, the model says the odds drop again until early 2027 when a new window opens over the Sun's northern latitudes. None of this means a superflare is coming. Forecasting a window isn't the same as forecasting an event, and the researchers themselves are careful to frame it as elevated probability, not certainty. The Sun might do nothing more dramatic than what region 4366 already did. Or somewhere in the southern hemisphere, in a region we haven't even identified yet, magnetic field lines could already be winding tighter than anything we've measured this cycle. What's changed isn't the Sun's behavior. It's ours. For the first time, scientists have a rough map of when and where to watch most closely, instead of simply waiting for the light to arrive and finding out after the fact. Whether that's enough time to matter, if the Sun does decide to aim something bigger our way before this window closes, is a question nobody can answer yet. There's a strange comfort and a strange discomfort tangled together in that. The comfort is that for the first time, we're not simply waiting in the dark. The discomfort is that knowing a storm season has started doesn't tell you which day the storm actually arrives or how hard it hits when it does. Region 4366 has already rotated off the visible disk by now, carried around the back of the Sun by the same rotation that brought it into view in the first place. It may come back around in a few weeks, weaker, or it may not come back at all. Either way, it's already served its purpose, not as the main event, but as a reminder of how quickly an ordinary sunspot can become a factory, and how easily a near miss can look, from the ground, like nothing happened at all. The Sun has spent all year giving us its warning shots. Whether it saves the real one for later is still, for now, an open question written somewhere in a sunspot we haven't seen yet.